Hello and welcome to this fifth and final passage from test number 2. Great job coming this far. I'm really excited for you because I know that you are going to do great things. If you're not feeling stronger yet, that's okay, that's normal. Most people take a little while before they settle in and get into a rhythm. So as long as you keep practicing these nuggets of wisdom that we've learned so far, you are going to do great. And you will get that invitation to that school you've been wanting to get into because your scores are going to be awesome. Now, I just want to dive into this and show you guys one more time how to navigate through another passage of the SAT. This passage appears to be a science one, and we have 75 lines. So yes, we will be applying those things again, as I just mentioned. We're going to be reading the excerpt, we're going to annotate as we go, we're going to chunk this passage, and yes, we are going to be using the My Answer strategy when we get to answering questions. Now, since we have 75 lines, I think we can chunk it right at 53 lines. And when we get to here, we can stop. So without further ado, let's go ahead and get started. The excerpt. This passage is from Geoffrey. Long a mystery, how 500-meter high undersea waves form is revealed. Some of the largest ocean waves in the world are nearly impossible to see. Unlike other large waves, these rollers, called internal waves, do not ride the ocean surface. Instead, they move underwater, undetectable, without the use of satellite imagery or sophisticated monitoring equipment. Despite their hidden nature, internal waves are fundamental parts of ocean water dynamics, transferring heat to the ocean depths and bringing up cold water from below. And they can reach staggering heights, some as tall as skyscrapers. So as far as annotating is concerned, we know that a few things. We know that these waves are underwater throughout. They don't break the surface. So no surface. Also, we learn that internal waves are fundamental parts of ocean water dynamics. They transfer heat to the ocean depth. So heat is sent downwards. And cold water is brought up. So let's keep reading from line 12. Because these waves are involved in ocean mixing, and thus the transfer of heat, understanding them is crucial to global climate modeling, says Tom Peacock, a researcher at the Massachusetts Institute of Technology. So in this region, we immediately learn why this is important to us, because we can use this in global climate modeling. So I'm just going to say global modeling just for brevity. And let's keep reading from line 16. Most models fail to take internal waves into account. If you want to have more and more accurate climate models, we have to be able to capture processes such as these, Peacock says. So why do we need to do this? Because we have more accurate models. Okay, let's keep going. From line 20, Peacock and his colleagues try to do just that. And what are they referring to when they say just that? They're referring to capturing the processes. Now let's keep going. Their study, published in November in Geophysical Research Letters, focused on international waves generated in the Luzon Strait, which separates Taiwan and the Philippines. Internal waves in this region, thought to be some of the largest in the world, can reach about 500 meters high. That's the same height as the Freedom Tower that's just been built in New York, Peacock says. So we learn here that they chose a location called the Luzon Strait because largest waves. I'm going to say largest, and I'm going to use a symbol for waves. Okay, let's keep reading from line 29. Although scientists knew of this phenomenon in the South China Sea and beyond, they didn't know exactly how internal waves formed. To find out, Peacock and a team of researchers from MIT and the Woods Hole Oceanographic Institution worked with France's National Center for Scientific Research using a giant facility there called Coriolis Platform. The platform, about 15 meters in diameter, turns at variable speeds and can simulate Earth's rotation. It also has walls, which means scientists can fill it with water and create accurate, large-scale simulations of various oceanographic scenarios. So it sounds like, although scientists knew that this phenomenon existed, they didn't know how the internal waves formed. So maybe we can put question marks here asking how waves formed. That's the question they're trying to answer, I believe. And then we learn here that the simulator they used has several features. So here we could just write simulator. Just in case there's a question asking about the simulator, we'll know where to go look for it. Now let's read on, starting with line 42. Peacock and his team built a carbon fiber resin scale model of the Luzon Strait, including the islands and surrounding ocean floor topography. Then they filled the platform with water of varying salinity to replicate the different densities found at the strait, with denser, saltier water below and lighter, less briny water above. So here we learn more of the experiment model that they built, and we learned that the saltier water is actually going downwards, and above the saltier water we have the less saltier water above it. So we'll just use a little graphic right here to illustrate that thought. Let's keep reading. beginning with small particles. Small particles were added to the solution and illuminated with lights from below in order to track how the liquid moved. Finally, they recreated tides using 2 large plungers to see how the internal waves themselves formed. So this is still experiment design right here. So we'll just be able to come back to this place if they're asking about how the experiment was conducted. And seeing that we've reached where we said we would stop and chunk this, it is time for us to go on and try answering as many questions as we can using those first 53 lines that we just read. Let's do that. Question 43. The first paragraph serves mainly to do what? So let's go back and read the first paragraph from line 1 through line 11. Some of the largest ocean waves in the world are nearly impossible to see. Unlike other large waves, these rollers, called internal waves, do not ride the ocean surface. Instead, they move underwater, undetectable without the use of satellite imagery or sophisticated monitoring equipment. Despite their hidden nature, internal waves are fundamental parts of ocean water dynamics, and I think that's the main part about this. Despite their hidden nature, internal waves are fundamental parts of ocean water dynamics, transferring heat to the ocean depths and bringing up cold water from below, and they can reach staggering heights, some as tall as skyscrapers. So let's go to the choices and read each one, see if we can come up with a good solution here. So choice A says, explain how a scientific device was used. Well, paragraph 1 didn't say anything about a device, so A is out. What about B? Note a common misconception about an event. There is no common misconception mentioned, so that's not it. C is describe a natural phenomenon and address its importance. Yes, that's pretty much what was said, but let's look at D just before making the final decision. Present a recent study and summarize its findings. Oh, D is clearly not correct. So C would have to be it. And yes, indeed, that was given to us by this crucial line right there. Let's go to the next question. As used in line 19, capture is closest in meaning to what? So line 19, capture is right here. Maybe we should read up a little bit just for context, starting with most models fail to take internal waves into account. If you want to have more and more accurate climate models, we have to be able to capture processes such as these. So capturing a process means to observe something, right? So let's look at the choice to see if there's anything alluding to observing. Control, no. Controlling and observe, no. So record, yes. Recording and observing, yes. You record and observe an experiment, so B could be it. Let's just look at the others. C says secure, no. And D is absorb, definitely not. So B would have to be the correct answer. Let's go to the next question, question 45. This is a detail / little picture question. According to Peacock, the ability to monitor internal waves is significant primarily because. Let's read that again. According to Peacock, the ability to monitor internal waves is significant primarily because what? Why do we want to have the ability to monitor internal waves? If you remember, this is something we actually annotated, I believe. We learned that if we can figure out how these waves are formed and how they move, we would have more and more accurate models, and that's something we annotated in this region, more accurate models. So perhaps we could read from line 12. Because these waves are involved in ocean mixing and thus the transfer of heat, understanding them is crucial to global climate modeling, says Thomas Peacock. So we see that they're crucial to global climate modeling. And then he goes on to say, most models fail to take internal waves into account. If you want to have more and more accurate climate models, we have to be able to capture processes such as these. So with that said, let's go over these choices and see if there's any one of them that agrees with what we are thinking here. So A says, it will allow scientists to verify the maximum height of such waves. That was never the goal. We didn't see any need to understand the maximum height of these waves. B is, it will allow researchers to shift their focus to improving the quality of satellite images. Definitely not mentioned. C is, the study of wave patterns will enable regions to predict and prevent coastal damage. Okay, that could be it, because models do predict, but we didn't see any mention about coastal damage, so maybe not C. Let's look at D first. The study of such waves will inform the development of key scientific models. It's got to be D. That's the whole point of conducting this research, is to be able to develop more accurate models. So D would have to be it. C is out. Let's go to question 46. Which choice provides the best evidence for the answer to the previous question? Thankfully, we've already annotated this, so we know that our answer came from this region, right in this blue region, and it appears to be line 16-ish. Yes, so C would have to be the correct answer. It's the only one that has those lines, 17 through 19. Now, let's go on to the next question, question 47. 47 is a vocabulary question. As used in line 65, device most nearly means what? Now, we haven't read all the way down to 65 yet. We stopped at line 55, which means it's now time to go on and just read the remainder of this passage. Let's actually do that, starting with this line right here. The Luzon Straits underwater topography with a distinct double ridge shape turns out to be responsible for generating the underwater waves. As the tide rises and falls and water moves through the strait, colder, denser water is pushed up over the ridges into warmer, less dense layers above it. So here again, if you're going to stop for a second, just annotate. We're learning that colder water is pushed up and warm water is pushed downward. So we keep going from line 59. This action results in bumps of colder water trailed by warmer water that generate an internal wave. As these waves move toward land, they become steeper, much the same way waves at the beach become taller before they hit the shore until they break on a continental shelf. So we know how these waves are formed is that this pushing up and down motion is creating the wave that came from this region. And then we can read on from 65, the final paragraph. The researchers were also able to devise a mathematical model that describes the movement and formation of these waves. And by the way, this is the question at hand. It said in line 65, what does the word devise nearly mean? The researchers were able to devise a mathematical model that describes the movement. So we can actually answer this question right now. To devise something is to build something. And if you look at the choices in 47, only A has a synonym, create, build, devise something. So all these other ones would not make sense. It's not solve, it's not imagine, it's not begin. Nevertheless, let's just keep reading the remainder of this paragraph, beginning with whereas the model is. So whereas the model is specific to the Luzon Strait, it can still help researchers understand how internal waves are generated in other places around the world. I think that's important. That's the whole point of modeling. It's that what you find from one location using that mathematical model, you can actually apply that same model to many other places. So I think this modeling everywhere. All right, so we go on from line 71. Eventually, this information will be incorporated into the global climate models, making them more accurate. It is very clear within the context of global climate models that internal waves play a role in driving ocean circulations, Peacock says. And that completes this passage. So we can actually continue answering questions. Thankfully, we've done 47 already. Let's go to 48. It's an inference question, so let's go for it. Based on information in the passage, it can reasonably be inferred that all internal waves do what? So let's go through the choices. Reach approximately the same height, even though the locations and depths of continental shelves vary. This passage is really not about height. The emphasis was not on the height of these waves, so that's not it. Based on information in the passage, it can reasonably be inferred that all internal waves, okay, so now let's look at choice B, may be caused by similar factors, but are influenced by distinct topographies of different regions. That sounds like a very viable solution. So that could be B. Let's leave that open. Let's check out C. Internal waves can be traced to inconsistencies in the tidal patterns of deep ocean water located near islands. This passage makes no mention of any such thing. Let's look at D. Internal waves are generated by the movement of dense water over a relatively flat section of the ocean floor. Nope, there was no mention of topography to this great detail, flat versus indented, and none of that stuff. So I think it would have to be B. And we know this is a fact because this region says, whereas the model is specific to the Luzon Strait, it can still help researchers understand how internal waves are generated in other places around the world. So let's go to question 49. 49 is an evidence-based question based on what we just annotated. So since we've already known and spoken of it being in this region, we can go straight to the choices and see, well, that has to be D, which is 67 through 70. So D would have to be it. A, B, and C are already out. Let's go to the next question, question 50. Data interpretation problem. In the graph, which isotherm displays an increase in depth below the surface during the period 1912 hours to 2024 hours? So which isotherm displays an increase in depth below the surface? Which one is going deeper down into the ocean between 1912 and 2024? So let's look at that graph. So ocean depth is on the y-axis and the times are up here. So we're focusing specifically between 1912 and 2024. So between here and here. The question is, which of those isotherms, 13 degrees one, 11 degree one, 10 degree one, and the 9 degree one, which of those is going deeper into the ground, into the ocean? It appears to be this one is going upward right there. This one's going upward. This one's going upward. So that leaves just this one that's going downward. It's going in the opposite direction. So these are the longer dashes, and these longer dashes are from the 13 degree centigrade one, which makes D the answer to question 50. So let's go to question 51, data interpretation problem. Which concept is supported by the passage and by the information in the graph? So let's read the choices. Internal waves cause water of varying salinity to mix. Well, the graph says nothing about salinity, so it cannot be A. Let's look at B. Internal waves push denser water above layers of less dense water. While that could be true, the graph doesn't give us that information. So we can't really say using the graph, so B does not make sense. Let's look at C. Internal waves push bands of cold water above bands of warmer water. That was definitely said in the passage. Can it be seen on this graph? We can't really tell where warmer and colder is in this graph. We see that the warmest water is up here, which is the 13 degrees centigrade, and the coldest water is down here, so that means C does not make sense. All right, well then let's look at D. It has to be D. Internal waves do not rise to break the ocean's surface. That is absolutely true. None of these waves, none of these four actually broke above the water. So this is the water surface right here at 0. So we can say without any shadow of doubt that D is the correct answer. And that was actually mentioned because they're saying in the passage and in the graph. In the passage, that was mentioned in the first paragraph. Right in this region, it says, unlike other large waves, these rollers called internal waves do not ride the ocean's surface. So that means the passage and the diagram both agree, which makes D the correct answer. So let's answer the last question, question 52. How does the graph support the author's point that internal waves affect ocean water dynamics? Let's read that again. How does the graph support the author's point that internal waves affect the ocean water dynamics? All right, let's go through the choices. Choice A says, it demonstrates that wave movement forces warmer water down to depths that typically are colder. So does the graph demonstrate that wave movement forces warmer water down to depths that typically are colder? Maybe. Let's look at B. It reveals the degree to which an internal wave affects the density of deep layers of cold water. It reveals the degree to which, no, B cannot be true because we don't have any way to measure the degree to which an internal wave affects the density of deep layers of cold water. So B is definitely not it. Let's look at C. The graph. It illustrates the change in surface temperature that takes place during an isolated series of deep waves. We know nothing about surface temperature. In fact, these waves do not break the surface, so we can eliminate C. Let's look at D. It shows that multiple waves rising near the surface of the ocean disrupt the flow of normal tides. It's not visible in this graph. You just can't tell. So it's got to be A. A is, it demonstrates that wave movement forces warmer water down to depths that typically are colder. Yes, there's this consistent downward movement, subtle but still there. And eventually the coldest water is on the bottom. So yeah, A would have to be the correct answer to this question. And that, dear friends, concludes test number 2, reading section at least. And I hope that you have enjoyed and learned as much as you possibly can. Please feel free to come back and re-watch these videos as often as you like. Remember those 4 types of passages and 8 types of questions. Please do remember the strategies that we have set forth. You're going to read the excerpt, you're going to annotate, you're going to chunk every passage, and you're going to use the My Answer strategy whenever applicable. And with that, I will be seeing you in the next lesson. Keep grinding, keep fighting, keep being awesome. See you soon.